We're happy to have Sam Buchanan speaking to us today. Sam this is Sam's second year at TTI, working on machine learning today. And today we'll be telling us about disentanglement and hybrid neural fields. I have no idea what that means. I'm looking forward to hearing about that.
Yes, so thanks, Nati. Yeah, this talk, I'm going to talk about some research and interesting collaboration I did in the last year. I think by the end of the talk, hopefully we'll understand what all of these words mean. But the project is going to be...
each word means. I just don't...
yeah, maybe the trigrams too. But this work is going to be kind of at the intersection of deep learning, machine learning, also kind of computer vision, and maybe even a bit like lower level stuff too. So I'm excited to tell you about this work. Let me start off with kind of like a high level, kind of from my viewpoint, where I stand, like the view of deep learning kind of in 2024. So from the practical side, I feel like it's more exciting than ever what we're seeing kind of capabilities of modern deep networks, ways we train them, data sets we train them on today. So if you think about different data modalities like language, kind of these very surprising emergent abilities of language models trained on kind of the internet and more. The way those are being used as foundations to build new models for kind of taking text prompts and generating photorealistic images, even maybe sort of 3D content too that's kind of capturing some aspect of the physical world. All this is really exciting. I think also for those of us who maybe hold like trying to do some math and mathematically understand deep learning, there's something a little bit, there's just a lot going on with these new systems. Things are being combined in new complicated ways. Often the ways that we're sort of demoing, evaluating these systems are different from the specific objectives we use to train them. And so things are getting complicated. I think for me, I personally feel that it's kind of in this context to kind of keep going forward with, understanding deep learning in terms of what it's being able to do in practice, at least to some extent. I think it's important, to take notice of these achievements. And at least to me, I feel like a lot of these achievements are being made possible because of the way that the sort of deep networks and these training objectives, in an implicit way that we don't fully understand mathematically, are able to capture the low-dimensional structures in different ways in these high-dimensional data sets that we're training them on. I think understanding this is sort of one of the most fascinating questions in this area. But it's sort of a bit hard to get started here because when it comes to trying to sort of model plausibly the types of low-dimensional structure that deep learning is maybe uniquely poised to exploit in these modern applications like photorealistic image generation, what have you, it's a little bit hard to think about what those models should be. So if we sort of dig into the toolkit of past sort of signal models kind of that we've used in certain contexts to design algorithms, you have kind of the tried and true model of signals that are sparse on basis, very popular 15 years ago. You could do a lot with that. Problems like the lasso, you can prove theorems about algorithms, you can build them, implement them, process data. When data are linear, piecewise linear, this works great. But sort of deep learning comes along in 2012 and blows a lot of these methods out of the water because in the real world, for data sets, sort of natural images, text corpuses, what have you, data aren't just sparse on a basis, they have structures that are different from these sorts of linear structures. So if you heard my research at TTIC talk last year, you'll know that I've sort of been thinking about this for a while. And one way I tried to, in some of my past research, kind of grapple with this question was trying to think about very general models for nonlinear structure. So in particular, what if data comes from a low-dimensional manifold, something that's very nonlinear, but nonetheless has certain properties, things that kind of intrinsically characterize the complexity of the data that we can use to try to understand algorithms like deep learning. And you can do some interesting work here. I think there's very interesting things to do still. But maybe the problem is that this sort of nonlinear manifold model is maybe even a bit too generic. So in terms of being able to use this to explain the success of deep learning in practice on some of the applications that we saw maybe in the last slide, maybe the manifold model and analyzing it is not giving us sort of the insights we need. So maybe a question, at least for me, and sort of in my research that I've been sort of thinking about, let's say since I've got here to TTIC, is sort of how to proceed in this question. So how should we model data? of all these successes in learning and try to analyze it and gain insights. So the project I'm going to talk about today is kind of an attempt to do this and sort of the angle is trying to take some inspiration from practice. And in particular, out of these many applications that I showed on the first slide. So one that I thought still is popular, although these things tend to come and go. But one thing that I thought was really cool, these sorts of data-driven methods, this is called NeRF, for learning to sort of represent the physical world. So we'll talk all about kind of what these methods do, how they work in a bit. But at a high level, you're sort of providing 2D images in a certain way to a deep network trained in a certain setup. And once you train that model, you can use it to render new 2D images of the physical world. I'm just showing this video because to me, when I saw this video back, a couple of years ago, getting into this area of learning vision, I just found this sort of a demo very exciting. It really feels like somehow in an application like this, maybe it's a little bit simple enough to be tractable, but just watching the video, it's kind of when we use deep networks to sort of represent data in this way, they're really capturing something intrinsic about the structure of the physical world, using that to render new images. And I felt like this would be maybe a good testing ground to try to figure out how to make progress on some of these questions about understanding structure or low-dimensional structures in data. So that's kind of the entry point into the talk. And from this perspective, kind of what we tried to do was turn the perspective of theory back towards practice a bit. So thinking about, are there any sorts of properties of data, visual data in these types of training applications that we can exploit in order to improve algorithms? So really trying to go both ways with the one. And so in the rest of the talk, I'll kind of describe this project that we worked on. It's called Tilted. So this is a new method for 3D representation. And I'll just describe some of the sort of theoretical studies that this project led to as well, trying to sort of get at this question of when we're trying to model visual data, what are certain maybe good model problems, structural properties that we can try to analyze, understand, and get insights in how deep learning might be working in practice. So for the structure of the talk, I'll spend a while talking about background. Bear with me just because I know we have a mixed audience here. Some people this will be very familiar to, others not, and in order to sort of motivate the developments later on to try to make sure we're all on the same page. And I'll talk about sort of the practical side of the method that we developed and also its theory. So for this method, I think the starting point, I want to describe kind of how NeRF works. So the method we developed is going to be a method for 3D representation and maybe NeRF for this type of application. So I'm sort of using NeRF in a way. Is maybe it kind of summarizes maybe a canonical framework in which you can think about what you use these 3D representations to do, how you combine them with data and stuff like that. So NeRF in its most basic instantiation is trying to solve this novel view synthesis problem. So you have a data set of calibrated images. So these are just images of a static scene. Assume it's not changing at all, like us, not us, maybe out in the hallway. Calibrated means that I know the position of the cameras for each image that I've taken. So I need this type of a supervision. And what I want to do is then be able to render new views of this static scene from new poses. And so this image from the original NeRF paper is kind of how that looks. If you're trying to render the drum, all these little square pyramids on the right represent a camera corresponding to one of the images of the drum taken on the left. And you have all this training data. You want to learn a model that can now generate new views of the drum. So there's a lot of different ways to do this. And I think, yes,
So could you just describe what is stored in I and T? I is the image and T in the training data. What is T exactly?
so I should be, yes, just an n by n by 3 image. And T, it needs to describe the camera pose, maybe other properties too, but let's at least say the camera pose. And what I mean by that is it needs to describe where the camera is in some sense. Where's its lens? That's maybe this circle on one of these pyramids. And then it needs to describe which way it's pointing. So that's kind of shown by how the pyramid is. So you can encode that in various ways. Maybe you need like 6 numbers for a redundant, that's not redundant, maybe for a minimalish parameterization of things.
Do you allow to change focus with your cameras, zoom in, zoom out, or not, or they are fixed, or it does not matter?
That's yeah. I think you should assume that's also part of T. So when
It's
I
part of
have
T,
these
right?
images in the data set, I also know sort of those parameters as what, like, that'll come in on the next slide, but what each pixel really corresponds to geometrically. And of course, once I learn the representation, we'll talk about that, but then I can try to render my new sort of, camera. So the way this problem works, I think I'll try to go into the details because I think it's like a really interesting example of like deep learning plus math plus modeling in practice that I was sort of surprised to see when I first saw it. So there's this complicated equation at the top of the slide. Basically, the way that NeRF proceeds is by saying, okay, the way I'm going to learn a representation for this 3D scene that I've rendered and all these training images that I have is I'm going to model kind of the process that generated each of these images. Sort of the physical process. And I'll use a really simple model to do that. I'll just imagine that sort of these images are captured in like a medium where I have sort of light propagating around. And so based on this type of model, I can derive that if I place a camera at some position in space and point a camera ray out of it corresponding to some pixel in the image, the light that's going to be incident, the light intensity that's going to be incident at that pixel is given by this certain integral kind of along the camera ray. And the integral involves quantities that are kind of properties of the light in the scene. So one quantity is kind of, the C here is sort of the color. Maybe there's different ways to encode this, but we can just think of what's the color of light at every point in the scene. Sort of, this is a map from spatial coordinates to colors. And we also have something here, which my understanding is that based on sort of the physical derivation, is like the absorption coefficient. It's often called the density. So this is kind of a measure of what is where. So at each point in space, maybe what is where is not precisely the right way to say it, but sort of what's the tendency of the medium at that point to kind of impede propagation of the light. So combining these sort of the integral equation here is kind of integrating this sort of accumulated transmittance along the ray here. That's kind of this inner integral here. The precise form isn't too important, other than the fact that it's not too complicated. And it sort of involves these two quantities, sigma and the color. And so the key idea of NeRF here is to say, okay, I have all these training images, and I know the camera poses that generated them as well. So what I'm going to do is I'm just going to set up an equation that kind of so it uses this rendering equation together with kind of replacing the color and this density sigma with the outputs of a neural network. So I'm just parameterizing color and density with the neural network. And then I'm going to train a simple L2 reconstruction loss.
Sorry, what's the input?
The input is just sorry.
I'm a bit confused. The input is C and sigma, or what?
So this, right,
What-
sorry.
in the for the neural net. I mean, I understand that equation, but what's the neural net mapping from to into?
So each C and sigma are both functions of 3D spatial coordinates.
Okay. So the
So in the
function C
most-
and sigma you're representing with a neural net. Excellent. Good.
Yeah,
I'm with you.
exactly. That parenthesis.
The function C and the function sigma.
Yeah, exactly. And so in practice, to get this to work well on real world scenes, you need more than just maybe spatial coordinates, but conceptually this is kind of maybe the most important thing. Just that this is sort of a map that's defined in sort of space. So with this rendering equation, now if I denote this sort of integral process with the camera rays on the previous slide, just abstractly by this script R, the way I'm going to, in the NeRF paradigm, train a NeRF is simply to optimize the parameters of some neural network F based on this reconstruction loss. So I just try to reconstruct all the images I have in my training set based on rendering the current value, the current representation for the 3D scene that's implemented by the neural network, given the camera poses that I have from the image. And I just minimize this with respect to the parameters in order to learn a 3D representation for this. Does this make sense? The interesting thing about this is that with the right engineering tricks, you can get this to work pretty well. So well enough to kind of make the entire field, maybe not the entire field, but a large percentage of the field, get very excited a few years back and start to kind of spur a lot of work on this problem. And I think, so NeRFs are a really nice example kind of the modeling that goes into training deep networks in these specific applications where you have very structured data. There are some limitations of them though. Maybe the main limitation, and so I'll talk a bit more about how this manifests. But one of the main limitations of the NeRF is just that all the information about the scene that you're learning is getting encoded in the weights of this neural network F. So this means that training can be pretty slow, inference might be a little bit slow, not too slow, but a little bit slow. And if you want to do downstream processing, maybe based on the scene that you've learned in this neural network, maybe try to edit it a bit, adjust lighting, things like that, it can be hard just because it's challenging to understand kind of the correspondence between physical properties of this 3D scene and the parameters of this neural network. So this, like to kind of dig into this a bit and motivate some of the later developments that came out of this, I will step back a bit and talk kind of more abstractly from a perspective that we can understand NeRF, I think, maybe a bit better. So this is thinking about voxel grid representations in space. So actually, I'll call these like a feature volume. So this is going to be like an alternate representation that I can use to sort of kind of render scenes in the same way that I can with NeRF in this training program. So what I need for a feature grid, I just need a discretization of space. So if I'm representing 3D scenes, I'll discretize them maybe uniformly like the cube. Kind of at each node in the discretization, I'll store some feature vector. So this is just some vector living in an abstract vector space. And when I query an arbitrary point in 3D space, just like I need to do in the NeRF, sort of in the rendering equation is what I need in order to calculate kind of the color of a pixel in an image, I will just interpolate in a certain simple way the different feature vectors that I've stored at each point in this equation. Does that make sense? So this is just a way to assign a feature vector to every point in space by interpolating features at discrete grid points. And then if I combine this representation, so now I can query any point in space, get a latent feature vector. If I combine this with what I'll call a decoder, just some map F, and you can even, we'll see this more clearly in a second, but you can even just think of F as a neural network. It could be a linear function. Just something that can map this feature vector to kind of, let's say in the NeRF application, colors and densities, what I need in order to render. Then the composition of those two things gives me a neural field, just the same as NeRF. So the problem with naive voxel grids is just that this is very expensive. So when we're storing, kind of the voxel grid idea is exactly what we're doing with images, right? When we store a pixel for every point in kind of a uniform discretization space. But in 3D spaces, just because of the dependence, which is kind of exponential, the dimension of the space we're trying to represent in, these things don't scale nicely. And besides that, kind of when you're using these to represent 3D space, most space is empty anyway, so it's very inefficient naively. So what people have done in kind of prior work to improve at this is to use kind of the analog of low rank grids instead of a full voxel grid. So I'll describe exactly what that means with examples. But let me just say abstractly before that, what a low rank grid entails is, whereas previously we kind of had a uniform discretization of 3D space, now what I'm going to do is I'm going to discretize certain like associated subspaces of the 3D space. And I'm going to have a map, maybe a set of maps that I'm going to call projections, which take kind of an arbitrary 3D point and project it onto these specific subspaces. So you can think kind of like in the picture here, maybe representing sort of the 3D space, kind of an analogy to a low rank factor UV transpose for matrices based on kind of an element-wise product of the elements of three different vectors kind of along the coordinate axes. So projection takes a 3D point and gives me features in these lower dimensional grids. Then I use the same sort of interpolation process in order to produce a feature that's associated to those projected points based on the discretized features in low dimensional grids. And then I have some kind of a reduction operation that takes each of the the interpolated features in these low dimensional grids and combines them into one overall feature that I can use for the latent representation. Yes.
How do you decide how to factor your grids and how many factors you need? Is it like, how do you do it during?
Yeah, often it's a practical thing because like I think for tensors, or at least once you go to dimension 3 and talk about factoring things in this way, there's no canonical notion of quantities like rank like there is in 2 dimensions. So I don't know, like if we really want to know, we can maybe go across midway and ask like lim. But my understanding is that there's maybe no right answer, and a lot of it depends on practice. So I think you just try, you experiment, and you see what other people have tried and see what works best. I'll talk about that. But the main advantage here in this framework, so again, I'll explain this with examples so it'll be much clearer. But the main advantage here is that now I can sort of trade off between complexity of the grid, so how many factors I use in these grids, how I partition up space, and the complexity of the decoder in order to try to make the representation more efficient, more compact, more interpretable in some way. Because these grid-based representations kind of are analogous to linear representations. They're very simple, easy to understand. So examples of this, maybe the easiest way or the simplest way to see that this is maybe sort of related to familiar notions is to think about low-rank matrices. So here, instead of representing kind of 3D space, think about 2D space. And so I'm going to talk about how to represent through this kind of interpolation paradigm or factored feature field paradigm, like a rank K matrix. So what that corresponds to here is that the latent vectors are going to be K-dimensional. So I'm going to have kind of, so in this paradigm, right, think of an image as kind of a function that's defined on the plane, kind of at the bottom left here. The grids that I'm going to use in this picture, or in this analogy, are sort of along the x and the y axes, kind of the natural coordinate axes of the image plane. These are going to be discretized uniformly, right? If I have an n by n matrix, they're going to be like that. And the reduction I'm going to use, so in this picture it should be clear maybe that the projection now is just going to take the xy coordinates and then give x, give y. So these are the projections onto the two 1D spaces. The reduction that I get, once I look up the corresponding feature value for each of these projected points, I just multiply them element-wise together. That gives me one rank K vector. And then I add up the components of that rank K vector to get it a single scalar. So that adding them up is like the decoder in this picture. That gives me the intensity. So this sort of shows how to think about kind of the usual way that we like to think, I think, analytically about low-rank matrices, maybe as a sum of vectors, UV transpose, being kind of exactly analogous to this factored feature field perspective. Just the difference is maybe in the factored feature field, kind of concatenating along differences. So we can think about NeRF in this way too, although this is sort of only an example with scare quotes. I think it's kind of instructive because this is sort of two ends of the trade-off here. So NeRF is kind of, now we're in 3 dimensions, but it's a lot like the low-rank matrix example, where the kind of the low-dimensional grids are just one-dimensional grids along each of the XYZ axes. Because NeRF, right, it takes basically the inputs, sort of XYZ spatial coordinates, and outputs the corresponding density and radiance at that point. So we have these 3 one-dimensional factors. Here we're not learning any features in this representation. You can think of it as just like there are fixed features for these low-dimensional grids. And the features are just the kind of the coordinates of the point along that dimension. The features are just XYZ after I project down. The reduction is concatenation, so I take those XYZ and I just concatenate them back together, and then I push that through the MLP. So this exactly describes how NeRF functions, and it is sort of is just emphasizing what I said before about kind of sort of NeRF representing everything about the scene, all the learning in the weights of this decoder F. So this is sort of like corresponding to the maximally simple encoding of the feature grid. And, so one example that's more practical that is actually being used a lot is this sort of triplane representation. So very simple, similar to the previous example, but now it's sort of an abstract feature feature grid where you have k-dimensional features. The low-dimensional grids here are a set of 3 two-dimensional grids that sort of coincide with the XY, YZ, XZ planes. Projecting down, just takes, an XYZ point and throws away the relevant coordinate. You interpolate the features, then you reduce them. So different methods were proposed to reduce in various ways. The methods that we're comparing to in the experiments in this paper are using a multi-point reduction. So just for each of those 3 planes, the k-dimensional feature that you interpolated, element-wise multiply them together to give you 1 k-dimensional feature, and that you put into your decoder. So when we talk about k-planes later as a baseline, this will be sort of what we have in mind. And this has been used most notably maybe in this method, EG3D previously. So this is kind of this notion of a low-rank feature volume, or what I'm going to call a high level, a hybrid neural field. Just sort of thinking of NeRF as the canonical neural field. And the hybrid neural field is kind of combining this MLP decoder with a kind of a low-rank feature volume representation for space. So you can trade off in this way between efficiency, compactness of the representation, and also interpretability. And so these methods have been used a lot in prior work, and sort of are quite popular.
So the k-planes, 3 planes, are just treated as additional parameters that are tuned with SGD?
Good. So our method will have a little bit of that flavor. I'll talk about that in a second. In the specific prescription here, they're not parameters. They're sort of just fixed. Like we decide that we like the XZ, the XY.
So but you're putting a feature vector in each pixel of each plane, if I understood right.
I think you can think of them as being indexed in that way. That's true. And those feature vectors are the trainable parameters. Yes, but they're sort of specific positional attachment. That's only relevant through the interpolation operation, if that makes sense. And those are fixed sort of kind of discontinued. Yeah. The questions? Okay, so since we've been through all the preliminaries, it's going to be straightforward now to describe kind of the core idea of tilted, what it does, how it works. So I'll show some of the results that we have from that. So the idea of tilted is that, so along with all the nice aspects of these sort of hybrid neural fields, the way they can be more compact, sort of be more interpretable, one potential drawback of them is that when you use them to represent real-world scenes, there's an issue that real-world scenes tend to have, for these types of linear low-rank representations, a preferred frame of orientation. And so that's just sort of, course, a consequence. And of course, it's not always true. But like I'm showing some photos I took this morning around TTIC. It's a consequence of the fact that in built environments, there's sort of lots and lots of like visual cues just based on kind of how we structure the world, gravity going down, buildings going up. In particular, you have all these points, lines, and planes. So these are like sort of very strong, regular, if you will, like in some sense, polyhedral structures that intuitively are much easier to represent with sort of a kind of a factored feature volume, whose coordinate frame is aligned with the intrinsic frame of these scenes. So in particular, in a room like this, I can represent with fewer components in the factored feature volume. If the projections for that factored feature volume are kind of aligned with the intrinsic frame of the scene. And it's not always true, right? Because scenes are not just, we're not just trying to represent the walls. We have plans, complex objects too. But these sorts of cues, I think they play a large role in efficiently representing these scenes. So if you're trying to be efficient, and of course, you always have a limited number of components to represent with your linear representation. This is something that can, play a role in performance.
Just I'm trying to wrap my head around. So this would be efficient if the objects are straight, but also only if they're axis aligned. Or if you have.
Yeah, that's the idea, and I'll talk more about that.
Okay, so
in a simpler.
So like
example.
that whiteboard, even though it's straight, even though it's flat, you is not efficient to represent because it's slanted. It's not axis aligned.
Yeah, that's the claim. So with a pure factored feature volume, of course you can represent things like this maybe with the MLP decoder as well.
No, sure, no, but with the factored representation.
Yeah. That's the claim. You will need more components to represent that.
Okay.
with a representation that's not aligned to that board's frame of reference. That's the claim. And so this is easier to see in sort of a toy example. So this square, we'll see it a couple of times, maybe more. So like the example of how this can play out negatively, if you're trying to sort of represent, now we're in 2 dimensions, an object that has a sort of a very strong preference for a certain frame of reference. And what I mean by that is that when you represent this square image in a coordinate frame that's aligned with the square, it's rank 1. So you can represent that with a maximally efficient feature grid. And it doesn't matter sort of the level of detail or the resolution of the image. It's always rank 1. So maybe the problem is that if you have an object, so the same information content, but that isn't aligned with the intrinsic frame of reference, so for example, for this square, now what you see is that the number of components that you need to represent the square perfectly, so with 0 error, it's going to start growing linearly and with the resolution, the level of detail, which doesn't make a lot of sense because sort of you want a representation like this, kind of want to use the available resources you have, this fixed number of channels, as efficiently as possible. And so in this case, if you increase the level of detail in the training data trying to represent high-dimensional images, this is telling you that you get like significantly less bang for your buck with the same model. So I think this is something that's pretty strongly undesirable, and kind of maybe the toy model manifestation issue I'm talking about. So tilted, what we do in this method is just have this very simple, of course there's many ways you can try to do this, but the idea is that we're going to try to incorporate canonicalization into the factored feature volume. So we're going to add sort of learnable transformations. So in the square example, of course, if you rotate the domain, right, incorporate this into the model, after rotation, you're going to have an object that you can represent with a single lowering factor. It's once again rank 1, and once again, this is sort of irrelevant of the level of detail. So we want to try to combine this idea, sort of bring it to bear in practice with these factored feature fields that we're talking about before. So the tilted approach is basically just to so take any sort of method for representing a factored feature field, like for example the K-planes that we talked about before. And what we're going to do is just add learnable transformations to the model. I'll sort of talk about how, but the basic idea is just that whereas previously the planes are sort of aligned with a fixed choice basis, maybe x, y, y, z, x, z, now the planes can sort of be allowed to rotate. So all we're doing in implementation is kind of rotating the points that we project on the planes. But you can sort of think dually as this rotating the planes that we're projecting onto.
Will there be a bias here that the planes are orthogonal? Indoor scenes tend to have orthogonal planes.
Yes, we'll preserve, so I'll talk about that momentarily. We'll preserve some of the good inductive biases of the methods like K-planes, using those 3 orthogonal planes. So the picture is a little bit misleading in that sense. I'll talk about that in a second. But yes, there will be. Because that's it. And so you can implement these transformations in a lot of different ways. We're going to use maybe the simplest possible, implementing rotations about the center of the planes. So just trying to capture a little bit of this effect that we saw with the square. You should be able to get much more out of more complicated transformations, but it maybe makes sense to get started with this one. So implementing this method, I'll just talk quickly about 2 details, not too many. So kind of to David's question, the way that we'll implement this, we'll say that kind of parameterize the flavor of tilted that we're using by the number of learnable transformations that we use. And we'll just pick that number as a parameter. And then, so kind of talking about any sort of method for representing 3D scenes that you have off the shelf, like maybe K-planes, and just say the final latent of that representation is K-dimensional. So we're going to partition that K-dimensional latent into a bunch of equivalent groups. So each transformation gets its own group. We'll choose the parameters, I guess, so that everything divides nicely here. So what that's going to mean is that if we're working with something like K-planes or a triplane representation that has 3 planes, so we'll divide there too. So these groups are not going to like split across pairs of orthogonal planes. They'll kind of divide evenly. And it'll end up being the effect of kind of each group having its own collection of rotations of a set of these points. And we use some regularization when we train these. Kind of the idea, and so this and the other implementation are both coming back to the issue that transformation optimization is kind of notoriously hard. So jointly optimizing a scene's appearance and kind of trying to adjust its pose through optimization. Very prone to get stuck in bad local minima. So you need to play use lots of tricks in order to get this to work effectively in practice, in order to not get stuck. So one of them is maybe with these groups, these can play different roles, right? One role is to represent different objects in a scene well that are posed differently to one another. Another is also just pragmatically maybe multiple tries, If you initialize your transforms randomly, they're not helping you very much. Using a group sparsity regularization can help you to try to suppress the effectiveness. So this is implementation detail number 1. And kind of in a similar vein, implementation detail number 2 is that we're going to sort of use some course-defined ideas in the implementation of this method. Again, because transformation optimization is so challenging and prone to bad local minimum in practice. So what we actually do is we use what we call this bottleneck phase of training, just a simple and natural idea, which is when we start training the sort of radiance field or what have you, we start out using sort of a capacity constrained factored feature grid. So we're not going to use maybe the most powerful K-planes or something like this. We use something like a CP decomposition. We'll train that for some number of steps together with an MOP decoder. We have the parameters of the grid, right? We have the parameters of the decoder. And we have the parameters of the transforms that we learned for our method. And then after we train those, we're going to throw away everything except the parameters of the transformations that we learned, and then do it again. So there'll be some additional course defined in there too. But the main idea of this is just that we want to try to get a good initialization of the final transformation parameters that we're going to use for the scene. So we'll do that by kind of beginning optimization with a capacity constraint representation, and then throwing away this sort of poor capacity representation, keeping the transforms, reinitializing, and learning the eventual model. So let me show some results for the method then. So those are the details. For more details, so we do have all the code released, and I'm happy to talk about it more too. So first, just getting a basic intuition for how the method works. It's maybe helpful, it was helpful to us in kind of running the project, just to test it on 2D images. So this is sort of a very toy kind of reconstruction task in 2D, where I'm only observing like a subset of the pixels of this overall Fox image, and then I'm trying to fit kind of a hybrid neural field to it, kind of like I would do in NeRF in 3D, but it's sort of a toy 2D version of that. And sort of the arrows in the plot on the right are kind of showing how the dynamics in a coarse way of the tilted method are working. So these arrows correspond to like the norms of the different feature groups that I have in the model. So it looks like I'm running tilted 8 here. I have 8 arrows. So the norms are like the length of these arrows. Each one corresponds to a group, to a transformation. And their length corresponds to like the norm of that corresponding feature group. So how much of a role is it playing in representing the Fox? Kind of what you see in the dynamics here is that the transformations that we're learning are kind of aligning themselves with the structure of the scene. So here the data that we're trying to represent is like a rotated image of this Fox. So these arrows being sort of aligned with this coordinate frame are corresponding to us learning those directions of the representation. In terms of details, this helps reconstruct some fine details in this example. So I won't talk about this too much, but we also, so these hybrid neural fields, you can use them for different sorts of neural field modalities. It's not just used for representing radiance fields like in NeRF. You can represent other types of fields as well. So these are some experiments with something called sign distance fields, where what you're trying to output is not like color and occupancy, but instead like signed distance to a surface in 3D space. So we show that using tilted in an application like this can review, together with like using marching cubes to render, can kind of reduce floating artifacts. In that sense, sort of helping capture the structure of the object better. So in terms of radiance fields, kind of evaluating tilted on real-world scenes, we see sort of qualitative improvements in terms of detail capture, kind of better alignment with the scene. These are some example scenes from the NeRF Studio real world scene dataset. Sort of details on the piano, on the dozer are captured better, sort of tilted is on the right, and the baseline K planes on the left. Sort of if we visualize some notions of interpretability or like how, not interpretability, but rather maybe how aligned the features that we're learning in our feature field are to the actual structure of the scene. So tilted has some improvements for that as well. So what I'm plotting here is sort of like kind of the norms of features at different points in the 3D space, those interpretable features. And you can see in representing this piano that tilted's features are kind of more aligned with the intrinsic frame of this piano scene. Similar for the Giannini Hall scene, kind of more a bit more aligned with the steps, kind of the building, whereas in the baseline, everything is sort of being represented all together. So you have most alignment. In terms of sort of plots, maybe the thing to highlight with these results, these are on synthetic data. What maybe this shows is just that, so with kind of the standard evaluation of neural radiance fields on these sorts of synthetic scene data sets, existing methods kind of have a bias towards axis line scenes. So when you're testing on synthetic scenes, you can always make sure the data is aligned with the coordinate frame. And we show that sort of creating an auxiliary data set where you just take the usual scenes but apply a random notation to the coordinate frame in which the object is represented. The performance of sort of baseline methods reduces by around 2-3 PSNR. So tilted could sort of be on par, improve a bit over these existing methods in the synthetic regime. Although this is sort of not, I think, what's a broader interest synthetic scenes. And kind of the takeaway overall for this result, I won't talk about this in too much detail, but these are all sort of the PSNR plots for the new NeRF Studio real world scenes data sets. And so what this is showing is that so tilted can be more efficient compared to baselines, sort of achieving similar PSNR to a baseline with sort of twice the number of channels across most of these examples, and always sort of achieving performance that's improved over the baseline with the same number of parameters. So in this sense, sort of aligning the features in this way with the extra parameters of learnable transformations is helping you to learn more compact representations for these real world scenes. Okay, so that's kind of the practical side. In the last part of the talk, I want to talk a little bit about some of the theoretical work we tried to do around this model, at least some of the model problems that we came up with. I'll talk through them quickly. So this is kind of like I'm presenting the talk sort of first the standard way, first the method, first the results, then the theory. But I think the nice thing about working on this project with these folks was that, sort of in terms of the theory helping the practice, it was really quite sort of a continuous interaction in terms of, theory actually being helpful in the development of this model. And I think one of the key ways you find that is maybe just that, like, when you're trying to build this type of a complex system, you need to debug things aren't going right. I mean, I'm not saying you need theory to do this, but it's sort of this type of mentality is very helpful in sort of cutting through what are the essential issues, figuring out what to try next, how to fix things. So in this project, I think this was sort of a very helpful aspect of what I'm going to talk about on the next slides. And so also, kind of in the context of thinking about sort of structural properties of visual data that we can try to model mathematically and analyze a bit, like we talked about at the start of the talk, kind of the design of tilted that we've talked about so far maybe suggests one sort of natural model problem here, which is for trying to represent these sorts of scenes that have kind of preferred coordinate frames of representation, and doing that with an optimization approach that sort of jointly learns pose and appearance. So these two aspects kind of the visual data, pose and appearance, we are sort of in tilted, sort of explicitly learning a disentangled representation because we explicitly translate or rotate the feature grids. And this is sort of maybe suggesting something that we could do some analysis of as well. So the model problem we ended up spending some time studying here was just based on this square. So trying to understand, like, does a method like tilted, that sort of jointly optimizes over pose and appearance. Like, is it possible for it to succeed in this type of context? So for this square, say I've rotated the square. So like, is this method morally correct? You know, simplest possible case. So if we set up kind of an optimization formulation for this problem, we can sort of represent it something like on the side here. So here this tau is just denoting sort of a rotation of the image, not a rotation in sort of the orthogonal matrix sense, but a rotation of like the image plane, so a rotation of the image content. And so the loss we can consider that's kind of a stand-in for tilted. This should be Frobenius, but it's just sort of the reconstruction error. So trying to learn some low rank factors, here I'll make them symmetric because I'm just talking about the diamond, UU transpose, such that when I rotate them, I reproduce the observation. And so I'll want here the parameter k to be small. What we see when we code up very simple models like this for this example of the diamond and square, so it does succeed every time. And so maybe with the theory here, we wanted to just try to think about, you know, for this extremely simple model problem, so what is actually giving rise to the success of this optimization? So why does this work? Try to get some insight into tilted based on that. So I'll skip this. So the first result that we prove here, this is a basic thing, just kind of verifying the heuristic from this example we talked about before about the rank of the diamond, or the rank of the square growing. So we talked before about how for perfect reconstruction, you need a number of components that grows kind of with the resolution, but in practice you don't really care about perfect reconstruction, you just care about reconstruction up to some specified level. So how do things scale there? So we sort of, it's definitely an artifact of the analysis that we sort of have a constraint on the number of channels of representation that work. But we proved here that you can have sort of a lower bound on the reconstruction error for any sort of pure feature grid based method that sort of scales inversely with the number of components in the representation. So this is sort of a limitation on the level, like sort of the PSNR performance that you can achieve with pure sort of factored feature grid methods, so no MLP. The way the proof works is kind of as you'd expect. So we use kind of the infinite dimensional model. This is maybe the part that's a little bit interesting for this square template. We just use perturbation analysis to argue that the actual image version of the square template, the diamond template, the sample version, kind of has spectral properties that behave the same as the infinite dimensional. And the challenge in doing this, which is maybe an interesting, unique challenge of kind of modeling working with images, is just the non-smoothness in the template here. So this is making the spectrum decay pretty slowly, necessitating, at least for me, certain technical arguments that are producing some artifacts. That's why there's this weird constraint on the target channel count that I can assert about. But the proof is just sort of perturbation in that sense, pretty simple, and by reduction SVD. So for tilted, I'll skip through the specific details of the argument for the interest of time, but I'll talk just at a high level. Kind of the algorithm we analyze for this optimization procedure is highly idealized just for sort of theoretical tractability, and still it's a bit technical. So we're going to use these four sorts of idealizations. We'll just consider how this algorithm proceeds this optimization in infinite dimensions, so I don't want to work with the discretization. We're going to work kind of in a critically parameterized setting. So there's a kind of an interesting connection here between implicit regularization and matrix factorization and the success of tilted in practice, because we're not explicitly asking to learn low-rank grids, but we still kind of learn them observationally. So this implicit regularization effect is sort of giving rise to that. But in this analysis, we're going to sort of trust that that can be proved and just work in sort of the critically parameterized regime. We'll also consider pretty artificial alternating minimization algorithms. So rather than updating the blocks together, update one of them. So that means the grid factors in a large block, then sort of rotate, then do the grid factors again. So this is just for sort of tractability. And instead of analyzing matrix factorization, so we just sort of reduce it to power method, sort of in infinite dimensions. I think this is just to avoid sort of technical complications with the matrix factorization landscape. So I will say the algorithm, but I don't want to go through all the details. So basically the idea is at a high level of just sort of, we'll start from random initialization, run power method, sort of in this, I'll talk about that momentarily. Run power method, so that's just updating the grid factors. After we have this initial estimate of the grid factors, we'll sort of update using gradient descent, the pose parameter of the template. And then once we've run that for sufficient time, we'll run another round of iterations of power method in order to learn the final. So the result that we prove here is sort of kind of in a regime working with constant step gradient descent on the pose parameters. Then sort of with reasonable rates, everything is sort of implicitly here kind of operating in low dimensions, so the rates are not something to worry about too much. Then with probability larger than 1/2, you would succeed with this algorithm in recovering sort of the parameters of the underlying square template, its pose, and its appearance, kind of up to symmetry. So that's sort of the guarantee that we can sort of just with one factor, with rotation, you can actually succeed in this problem. And so the interesting aspect of the proof here, which is something I didn't kind of appreciate before we did this analysis, is it kind of in classical kind of registration methods where you try to learn a transformation to match observed data to some template. Very standard thing to do is use Gaussian smoothing, just in order to sort of operate from a coarse-defined way. So starting from very coarse features of the images, match those, and then restart with smaller and smaller levels of smoothing until you succeed. Something that's interesting that happens with these low factored grids is that there's kind of an implicit coarse-defined regularization. Because if you have a poor estimate of the parameters, the pose parameters of the template, you can't use your capacity fully to represent because your capacity is fixed at some maximum.